12th class, chapter 3, current electricity, 13th session. And that's about the backbone of this chapter. Actually, if you take mechanics, conservation of energy is the most important principle behind mechanics. If you take refraction, Snell's law is the basic of it. Just like anything, the most fundamental law or the most important law in current electricity is Kirchhoff's law. And Kirchhoff's law has two parts. Kirchhoff's law, Kirchhoff's law has two parts. One is Kirchhoff's current law and the other is Kirchhoff's voltage law. Okay. This video will be for Kirchhoff's current law. What is Kirchhoff's current law? Kirchhoff's current law. I will draw one circuit, one random circuit I will draw. There are resistors like this. Okay. Let me draw a circuit like this. Anyway. Okay, something like this. It's a circuit. There are so many resistors, R1, R2, R3, R4, R5, etc. So many resistors are there. And you know, current will start to flow from this battery. And current will reach at this junction, isn't it? This is what a junction is. This is not a junction. This is only a bend. Just like in a road, junction, you know, where so many roads meet. Just like this is a junction. It's only a bend. This is a junction where so many roads meet. It's not a junction. This is a junction. So all these are the junctions. Let me call the total current I comes here and it splits into two at this junction. Let it be splitting as I1 and I2. And this I1 will enter this junction. There again it splits. It's I3 and I4. Now what happens? I2 comes from this way, I4 comes this way, and at this junction they adds and moves as I5. Now this is again a junction where I3 comes, I5 comes, and finally all these are added to get I again. This is what is happening in a current circuit. So I can say there are different junctions, J1, junction 2 and junction 3. And the Kirchhoff's current law is applicable for junctions. So it's otherwise known as a junction rule. It's otherwise known as a junction rule. The rule is very simple. Actually very simple. What? Algebraic sum of the current at a junction is 0. If you take a junction, the sum of all current at a junction is 0. Algebraic sum of current at a junction is 0. Actually, what do you mean by that? The total current entering will be equal to total current leaving, so that no current exists in the junction. No current exists in the junction. That's what it means. Or there is no charge residing at the junction. No charge is residing at the junction. The total number of charges or the total charge flowing is conserved. There is nothing residing anywhere. So if you take a junction J1, you apply algebraic sum of current equal to 0. What are the current at junction J1? Current at junction J1 are I, I1, I2, and when you add all these, the sum equal to what? 0. And what about junction J2? Junction J2, different current entering are I1 and I3, I4. The sum of all these junctions, the sum of current at all these junctions is equal to 0. Now what about at J3? At J3, you can say there are different current associated with J3, and that is I4, I5, I4, I5, I2, and sum of all those current equal to 0. Finally, what is for J4? Junction 4, the current at J4 are I3, I5, and I. These are the current at junction J4. Sum equal to 0. This is the low, but I wrote it wrong. I wrote it wrong here. So what is right? I wrote it wrong here. What is right? So before we apply this law, we have to adopt a sign convention. And what is that sign convention? See, for any junction, there are two types of current. One current is entering the current, the current entering the junction, and other is the current leaving the junction. Okay, for this one, I is entering and I1 and I2 are leaving. So you have to apply a sign convention. The sign convention is very simple. Current entering the junction is taken as positive and current leaving the junction is taken as negative. Then the equation or the junction rule will be complete. Current entering the junction is positive and current leaving the junction is negative. So if I say I entering, I1 and I2 are leaving. So we have to apply negative. Okay. Now at J2, I1 is entering, I3 and I4 are leaving. So you have to apply negative there. Now what about J3? J3, I4 and I2 are entering. I4 and I2 are entering. I5 is leaving. So we have to put negative I5. What about J4? At J4, I5 and I3 are entering and I is leaving. So we have to put negative sign on I. So I will conclude. Kirchhoff's current law states that at a junction, the algebraic sum of the current is 0. When we apply the law, we have to adopt a sign convention, and the sign convention says that the current entering the junction is taken as positive and current leaving the junction is taken as negative. And the same equation you can redraw it like this. Here I equal to I1 plus I2, right? Here I1 equal to I3 plus I4, right? Here I4 plus I2 equal to I5, right? Here I3 plus I5 equal to I, right? So what happens now? I equal to I1 plus I2. So I equal to entering current and I1 plus I2 equal to leaving current. So Kirchhoff's current law can also be expressed in another way, like sum of current entering junction equal to sum of current leaving junction. This is one another way of writing current law. So this is the current law, and current law is a consequence of conservation of charge. Kirchhoff's current law is a consequence of conservation of charge.